In the last lecture, we introduced mutation as a component of our data structures. We saw, for example, that setBang was a way of changing the value associated with the variable, and setCouldrBang and setCarBang were ways of changing the elements of a list structure. Now, several important things happened when we introduced mutation. First, we introduced the notion of time and context into our interpretation scheme. The order in which things were evaluated now mattered in terms of the kinds of values we saw coming back out. As a consequence, secondly, we shifted from a functional programming perspective to a more state-based programming perspective, a point we're going to come back to. Third, we unfortunately introduced the opportunity for bugs and errors, since shared objects allow mutation of one to affect the value of another. And we're going to come back to that point as well. And finally, fourth, we broke the substitution model. Now, this last point needs to be addressed, and indeed in addressing it, we're going to address many of the other points I've just raised. And so today, that's what we're going to do. We're going to replace the substitution model with a stronger model that incorporates the substitution model as a piece of it, but also accounts for state, time, context, and mutation. Now, to stress this point, to stress the idea that the substitution model no longer works, take a look at this code. Why does it behave this way? We can see that makeCounter is a higher order procedure. It's a procedure that returns a procedure as value. But notice that if we create a counter called CA, and we call it several times, it simply increases its value by 1 each time it's called. Thus, the standard substitution model, the functional programming model, doesn't hold, because evaluating exactly the same expression, open paren CA close paren, is leading to different values depending on when we actually evaluate it. Secondly, if we create a second counter, defining CB to be the value associated with evaluating makeCounter, which itself is the same expression that we got when we defined CA, we end up with different structures. Calling CB and then CA shows that the two are independent. They don't behave as if they were shared in any way. So, our substitution model is broken. Mutation has caused that to happen. We need to come up with a better model to explain how code like this works the way it does. To do this, we're going to introduce a better model of evaluation, and this is known as the environment model. This model will both explain mutation as well as standard things that were explained by the substitution model, and it's going to lead us towards a much better understanding of the notion of evaluation in general. So what is the environment model? Well, for now, you should think of it as a very precise, very mechanical description of a set of rules for determining the values associated with the expressions. Similar to what we saw earlier, we'll see a rule for dealing with getting the value of a variable, a rule for creating definitions of variables, a rule for changing the values of variables, a rule for creating procedures, and a rule for applying procedures. But the key issue is it's a very mechanical, precise description of exactly how values are associated with expressions. So our goal will be first to determine the specific rules for the environment model for these kinds of expressions. Once we've set out those details, we'll be able to explain the evaluation and evolution of arbitrarily complex code, including things like the example we just saw. More importantly, by using the model to analyze code, we'll learn how to associate particular coding choices with their effects, and thus we'll be able to work the other way around. Having decided what behavior we need for some problem, we'll be able to create appropriate code, including code that involves mutation as well as normal functional kinds of programming. And we really have two reasons for doing this. The first is, in fact, just to deal with understanding what happens when we make choices in our code, to deal with the ability to have side effects and mutation in our language and understand how to control it. But ultimately, we're going to see that, in fact, the model we'll build, this environment model, is the blueprint for building an interpreter for scheme. That is, the guts of the code that actually allows us to evaluate any expression, the thing that makes scheme run. As a consequence, for now, certainly starting today, we're going to draw an environment model somewhat abstractly, using various sort of notations and graphical manipulations to deal with what's going on inside of it. But we'll see that, in fact, it leads to a very mechanical idea that can be, in fact, implemented in code, and we'll do that in a few lectures' time. As we build up the pieces of our environment model, a key thing to keep in mind is that we're about to shift our viewpoint on what constitutes the basic units of computation. Until we introduced mutation, we could think of a variable as just being a name for a value. That was exactly how it behaved in that sort of functional viewpoint of computation. Now we're going to change that viewpoint. We're going to think of a variable as a place into which one can store things, a name for a placeholder or a box or a cubicle into which things can be placed. The second change we're going to make deals with procedures. Up until now, we could really think about procedures as if they were functional descriptions of some computation. We stressed this idea that evaluating the same expression gave rise to the same value. It behaved as a mapping from input values to output values, like any ordinary function would. Now, we're going to change that view. We're going to change our view of procedure to instead think of a procedure as an object with an inherited context, a context that tells us how to interpret symbols in that computation. And that's going to change the way we think about computation overall. And finally, we're going to change the way we think about expressions. We're going to now say that an expression only has meaning with respect to a structure called an environment, something we're about to build. But this means that expressions now inherit their interpretation or their value by inheriting information about what was going on when they were created. And we'll see why that changes our viewpoint of computation as we go through the rest of this lecture. So we ask you to keep those three things in mind as we now build up this new model of computation. Variables are now places into which one can store things, procedures are now objects with an inherited context, and expressions have meaning with respect to an environment. So now let's start building up our environment model. First of all, if variables should now be thought of as places, we need a way of organizing them. So the first piece of an environment is something we call a frame. This just consists of a table of bindings, and a binding here refers to a pairing of a name and a slot into which a value can be stored that will be associated with that name. In terms of an abstract schematic for keeping track of that, here's a table of bindings. Table A, which we also refer to as a frame, has two bindings in it. It has a binding for the variable x and a binding for the variable y. And in particular, we say that x is bound to the value of 15 within frame A, and y is bound to the value of the list 1, 2 within frame A. Notice that the value of the variable within this frame is therefore given by the value of 15. Or a better way of saying it is, the expression x has a value associated with this frame, and it's the value obtained by looking up the binding of x with respect to this table. In a second, we'll talk about how we actually establish bindings in these frames, but for now we've got the first piece of our environment model. A frame is a table of bindings. A binding is simply a pairing of a name and a value. Now, an environment consists of a sequence of frames, for reasons that we'll see shortly. So here's our frame from before with the bindings we had, and here's a second frame with its own set of bindings. Now, an environment is a nested sequence of frames. So environment E1 will consist, in this case, of frame A followed by frame B. A second environment, E2, might just consist of frame B. So note that a frame can be shared by several environments, and in fact we'll see why that's going to be a very powerful thing in a few slides. The connection between frames is important and is called an enclosing environment pointer. So for example, E1 starts with frame A and inherits frame B as the enclosing environment, which in fact is similar to E2, or that environment. We'll see shortly why all of these pieces put together make us understand exactly how evaluation is going to proceed. Now so far we've just been talking about details. We've got frames, which are tables of bindings, we've got connections between frames, we've got environments as sequences of frames. With all of these pieces in mind, we can now start relating them to the actual evaluation of expressions. Now we're ready to see how to connect environments to evaluation. First, as we've already suggested, all evaluation is going to take place with respect to some environment. That's going to be the place that provides the context for how to interpret symbols and names. Notice that this won't always be the same environment. And in fact, a key issue is that whenever we apply a procedure, we will create a new environment which captures the context for interpreting the variables of that procedure. Now we've said all evaluation of expressions is going to take place with respect to an environment. And we've also seen that environments can inherit other environments as part of the chaining process. Nonetheless, this means that eventually we have to have some way of stopping that chaining of environments. And to terminate that chain, we have a special environment called the global environment. It has no enclosing frame and is the only such environment with that property. This is the environment in which we will normally evaluate expressions. It's our starting point, and it's going to hold the base set of expressions for our language. So we're ready to start putting together rules for evaluating expressions with respect to environments. Before we do, let's remind you that our central rule for evaluation dealt with combinations. And in this new model, things are nearly the same as they were in the substitution model. As before, we will evaluate the sub-expressions, now with respect to the current environment, and then we're going to apply the value of the first sub-expression to the values of the others. We'll see shortly how to do that in a very mechanistic way, but it says that basically our combination rule is going to be very similar to what we did before. With all of this in place, let's actually start building the environment model then. Okay, we're ready to start looking at our rules for evaluation in this new model, and in particular relating them to the environment model and how environments are created and manipulated. First, the simplest possible expressions in our language are numbers. These are self-evaluating, which means their value is just their value, no matter what the environment is, so there's nothing really much to say about them. The first interesting rule comes with names. We have a way of dealing with evaluation of names, our simplest kind of primitive, and that rule should tell us how to get the value associated with a variable. The rule is straightforward but quite mechanistic, so let's say it clearly. A name x evaluated in environment E gives back the value of x in the first frame of E where x is bound. Remember, an environment is a sequence of frames, so we will start in the first frame and look for a binding of that name and continue up the frames until we find the first such binding, in which case we return the value associated with that name. So here are our example environments from before. We'll call the top level environment the global environment. It's our stopgap environment. And E1 has its own frame and inherits as an enclosing environment pointer the global environment. We can now talk about the value of a variable with respect to an environment. And in fact, we should always talk about values of anything with respect to some environment. So for example, we can ask what is the value of the variable z with respect to the global environment. And notice the little notation I'm going to use here. I'm going to give the expression and then a vertical bar to indicate that I'm doing the evaluation with respect to some environment, and then a subscript notation to indicate that in this case I'm asking for the value of z with respect to the global environment. Note as well, that would be the normal place in which I would type to the computer. If I type in z at top level, it's talking to the global environment, and I'm going to do the lookup there. Our rule we can now use. The value of this variable z with respect to the global environment is clearly 10. That's the pairing associated with it. If I ask for the value of z with respect to the environment E1, I start in frame A, the first frame of that environment. There is no binding for z available there, so I move up the enclosing environment pointer to the next frame, in this case frame B, and ask for the binding of z there. In this case there is one, and I return again the value 10. Finally, if I ask for the value of x with respect to global environment E1, it points to the first frame A. I look for a binding of x there, and having found one, return the value 15. On the other hand, if I ask for the value of x with respect to the global environment points to frame B, so I start there. I have a binding for x in that frame, and I return therefore the value associated with it, which is the value 3. In this case, we can see that x has a different value in different environments. In E1, its value is 15. In global environment, its value is 3. And we say, in fact, that the binding of x in frame A shadows the binding of x in frame B. It hides it, so that when we start in frame A, or environment E1, we only see the binding of x to 15. Nonetheless, we now see how the name rule tells us the mechanism by which we look up the value associated with the variable in some environment. Okay, we have a rule for looking up values associated with variables. Now, what about the rule for creating bindings of variables and values? Of course, that's a define expression, and we have a rule for dealing with that. A defined special form, when evaluated with respect to some environment E, creates or replaces a binding in the first frame of E. And it always does it in the first frame of E. So here's our environment structure from before. Let's look at what defines do when they're evaluated with respect to this environment structure. First, let's suppose we evaluate define of z to 20 in the global environment. As I said before, this would be the kind of thing you would type into the computer. You're dealing with the global environment. This is an expression you might normally evaluate. What happens? Well, note what the rule says. It says create a binding or replace a binding for the variable, in this case z, in the first frame of the environment, in this case the global environment. So that old binding for z as 10 gets replaced by a new binding of z equal to 20. On the other hand, suppose we evaluate a defined statement of z to 25 in the environment E1. What happens in this case? Well, remember our rule. It says create or replace a binding for the variable in the first frame of the environment. So in this case, we do it in frame A, the first frame of environment E1. And since there is no current binding for z in that frame, we create a new one. And we've now set up a shadowing of z. The z bound to 25 in frame A will shadow the binding of z to 20 in frame B, similar to what we saw in the previous slide. Now, we have a rule for looking up values of variables. We have a rule for creating bindings of values and variables. We also should have a rule for dealing with mutation of variables. That'll be our setbang rule, our mutator rule. And here the rule is as follows. Mutating a variable x, doing setbang on it, if we evaluate such an expression with respect to an environment E, it changes the binding of x in the first frame of E where such a binding occurs. Look at this carefully. It's different from define, and we want to show exactly why. So here's that environment structure we had before. Let's look at what happens when we evaluate setbang expressions with respect to this structure. So let's evaluate setbang of z to 20 with respect to the global environment, and let's see what happens. Well, the rule says find the first frame in this environment in which there's a binding for this variable. We're doing it with respect to the global environment, and there is such a binding for z, so we change it. In place of z, we take the value of 20 and substitute that in, causing a mutation. Notice, if we look back at the previous slide, the effect here is exactly the same as a define. So why do we have two different forms? Well, let's evaluate set bang of z to 25 with respect to environment E1, and let's see what happens now. Remember what the rule says. It says starting in frame E1, find a binding for z. There isn't one in frame A, so we go up the enclosing environment pointer to frame B. Fortunately, there is a binding for z there, so we change that binding. That is, we actually change the value in the slot associated with z, removing the old value of 20 and replacing it with the new value of 25. Compare this to what happened when we did a define on the previous slide. Notice that now the change has taken place in a different spot. Set bang always looks for an existing binding of a variable, walking up the chain of frames until it finds one, and then changing or mutating that value. Define always creates a binding in the current frame, even if there was a previous binding there. Okay, let's see if you're getting these ideas. Here are a set of expressions that we'd like you to evaluate in order. Take a second to see what each one of them does, then click on the mouse button to see what the actual expression should be or what the effect should be in each case. Well, the first one's straightforward, but let's do it very carefully. Evaluating this expression with respect to E1 says, get the value of z, which we start in E1, and move up the frame until we find a binding, which happens to be 10. Get the value of 1, which of course is 1, and then add them together to return the value 11. Doing the mutation of z with respect to E1 says, first, get the value of plus z1 with respect to E1. Just did that. We know it's going to be 11. And then it says, starting in E1, or frame A, find a binding for z. There isn't one in A, so go up the enclosing environment pointer to frame B. There's the binding for z. Change it to the value we just evaluated, namely change that 10 to 11. Now, let's do a define with respect to E1. Remember, we get the value of the sub-expression plus z1 with respect to E1. And just as we did before, we start in E1, there's no binding for z there, we go up the enclosing environment pointer, find the binding for z, which is now 11, add that to the value of 1, which is 1, giving us 12, and then create a binding for z in E1. Notice where that happens. We create a pairing of the variable z and the just computed value 12 in E1, or in particular in the first frame of E1, frame A. And the last one we tried to sneak by you. We can still get the value of plus z1 with respect to the global environment. That's just going to be 12. But trying to do a set bang of y with respect to the global environment will fail. Note, we start in the global environment looking for a binding of y. There isn't one there, but there's no other enclosing environment to go up to, and so we have an error. We cannot create that binding. Remember, we never see the binding for y with respect to the global environment. That's down in E1, and that's not accessible to us because there are no enclosing environment pointers getting to that point. Next, we need to deal with lambda expressions. And here we see a big change in our view of evaluation and computation. First, we're going to introduce a more explicit notion or notation for the procedure created by the evaluation of a lambda expression. If we go back to our two-view world, which we used when talking about the substitution model, remember that we said evaluation of a lambda using its rule created a compound procedure in the evaluation world, and that gave a printed form that identified it as such back in the visible world. In the environment model, we're going to be much more explicit and mechanistic about what it means to create a compound procedure. And in particular, we're going to create a notation for it called a double bubble. This object contains two parts. The first part, or the first bubble, points to the actual code associated with the procedure. And it will indeed have two parts, the formal parameters of the procedure and the body of the procedure, just as we saw inside a lambda expression. Note, by the way, that the body of this procedure, times xx in this case, is just list structure. It has not yet been evaluated. We have no value associated with it. It is simply copied across as the code associated with this part of the double bubble, or the new procedure. The new part is the second bubble, and it points to an environment, and in particular to the environment in which the lambda expression was actually evaluated. This environment pointer captures a context, the context that was in place when the lambda procedure was evaluated, or rather the lambda expression was evaluated, or if you like, it captures the context in which the symbols of the code of the lambda will be evaluated. Now we can actually define the lambda rule for evaluation in our environment model. We know that this should create a procedure object. The key is that the environment pointer now points to the current environment. And let's look at what this says. It says a lambda special form, when evaluated with respect to some environment E, creates a procedure whose environment pointer is that environment E, and obviously whose code pointer should point to the body of the lambda itself. So let's look at this in more detail. Here again is our environment structure that we've used in the previous examples. And let's look at what happens if we actually evaluate a lambda expression with respect to this. In particular, let's evaluate this define of square to be lambda of x times xx, all with respect to environment E1. And let's start with the lambda itself, the inner part. Well, the rule says evaluate this lambda with respect to E1. So that will create one of these procedure objects, this little double bubble. The code part of it points to the formal parameter x and the body times xx. And the environment pointer, we also know, should point to a very particular place. Specifically, it should point to frame A, because the lambda was evaluated with respect to E1, and E1's first frame is frame A. So notice, this rule, very mechanistically, always tells us where the environment pointer should go to. That's the context in which lambda was evaluated. That's the context that will define how to interpret other symbols within the body of the expression. The next important point to note is that evaluating a lambda actually returns a pointer to the procedure object. That is, evaluating that red lambda expression returns as its value a pointer to that double bubble. It actually has a handle on the procedure object that was created. Why is this relevant? Well, because we can now complete the evaluation of the define expression. Remember what a define should do. It should create a binding for the symbol square in frame E1, or the first frame of E1. And what should the value be associated with square? The value returned by evaluating the lambda expression. So we will literally create a pairing of the name square in E1, or the first frame of E1, with the actual procedure object. Now comes the big change. Remember, the central part of our evaluation model is how to apply a compound procedure to a set of arguments. That is, how to apply a procedure we've created using a lambda to a set of arguments to execute some computation. We saw that in the substitution model. Now we need to define it for our new model, the environment model. And it has basically 4 steps. To apply a compound procedure to a set of arguments, you do the following. Step 1, you create a new frame A. Step 2, you convert that frame into an environment by taking A and having its enclosing environment pointer go to the same frame as the environment pointer of the procedure P. That's very important. It says frame A will inherit the same environment as the procedure inherited. Step 3 says within frame A, you take the formal parameters of the procedure and you bind them to the argument values that were passed in. And then finally, step 4, you evaluate the body of the procedure with respect to this environment E. This is the central step of the environment model. And these 4 very mechanistic steps are absolutely essential. And as it says here, you really need to know them. You need to be almost Pavlovian in your response, that whenever you apply a procedure to a set of arguments, you create a frame, scope it with the environment specified by the environment pointer of the procedure, within the frame bind the parameters to the argument values passed in, and then reduce that entire compound expression evaluation to the evaluation of the body with respect to a new environment. Because this is the central part of the environment model, let's look in very painful detail at an example of an evaluation. In particular, let's look at the evaluation of square of 4 with respect to the global environment. And here's the structure I have. Let's assume that x has already been bound to the value 4 by some defined statement within that environment, and we've created the definition for square as we just saw. It's pointing to that procedure object. Now, what we want to do is see how the rules for the environment model tell us how to get the value associated with squaring 4 in this environment. Well, this is a compound expression, so the first thing says we have to get the value of the sub-expressions with respect to the global environment. 4 is easy, it's just self-evaluating. We also need to get the value of square with respect to the global environment. And that we also know how to do. That's just the name rule. We look up the value or the binding of a square in that environment, and it simply points to that procedure object. So it's going to print that back out, but what it really says is we have now a binding for square. We've gotten back the value, which is that double bubble shown in the diagram. Aha! We're applying a procedure, one of those double bubble things, to a set of arguments. So our 4-step rule now comes into play. Step 1, create a new frame. Let's call it A. Step 2, convert that frame into an environment by having its enclosing environment pointer point to the same environment as the procedure's environment pointer pointed to. In fact, notice this nice little notation I can use. I can link these 2 pointers together to remind myself that the enclosing environment pointer of frame A, or environment E1 if you like, comes from the same enclosing environment pointer as the procedure whose application caused frame A to be created. Step 3, take the formal parameters of the procedure being applied, in this case x, and bind them within that new frame to the value of the argument passed in this case 4. Now, with respect to that new environment, E1, evaluate the body of the procedure. So notice, evaluating square root of 4 with respect to one environment has reduced to evaluating a simpler expression, in this case times xx, with respect to a new environment, environment E1. Now, the same rules apply as before. This is a compound expression, so we need to get the values of the sub-expressions with respect to E1. And we start with getting the value of times, or star, with respect to E1. Star certainly isn't defined within frame A. That frame came from the application of the procedure, and only formal parameters are bound there. So our rule says, go up the enclosing environment to the global environment and look for a binding of star there. Well, we didn't tell you this, but in fact the global environment creates bindings for all the basic built-in procedures. So in fact star is bound to the primitive procedure up in that environment. And therefore our name rule looks up the value associated with star and returns it. So in this case we do get a value associated with star. Now remember where we were. We were getting the value of times xx with respect to E1. We got the value of the first sub-expression star, or times. Now we need to get the value of the next sub-expression x with respect to E1. Notice this is just the name rule, and it says, starting in E1, look for a binding for x. There is one there, so we get back the value associated with that frame. In particular, we get back the value 4, not the value 10 that is up there in the global environment. We start in this frame, E1, looking for the binding, and since there is a binding there, it shadows the further binding down the streams. And now we complete this. Similarly, we get the value of the second x with respect to E1. That again gives us back 4. And now we're left with the application of a primitive procedure to two simple values, 4 and 4. And that will, of course, return the value of 16, which is the value that we return for the entire expression, since we reduced square root of 4 with respect to the global environment to times xx with respect to E1. I know this was a long example, but notice how the mechanistic rules of the environment model simply tell us how to follow through the evaluation of an expression with respect to an environment, reducing it to simpler things and getting out the values we expect. Now, let's be slightly more daring. Having seen the application of a simple procedure like square, let's look at something that involves a little more work. In particular, let's assume that we have defined both square to be the procedure we expect, and we define increment square to be a procedure of one argument that adds 1 to the square of that argument. Here's the structure we would expect for the environment. So let's check it out. Let's evaluate increment square of 4 with respect to the global environment. And here's that global environment we just created. We have bindings for square and increment square to the two procedures as shown. As in the previous case, this is a compound expression, so we need to first evaluate the sub-expressions with respect to the same environment. Value of increment square with respect to the global environment, that's just the name rule. We look it up and get back that double bubble, that procedure that is pointed to by the actual binding. And as we saw before, our 4-step rule kicks in. Step 1, create a frame. Step 2, turn it into an environment by having the enclosing environment pointer of the frame point to the environment specified by the procedure that's being applied. And that we know is specified by the second part of the double bubble of the procedure we're using here. Step 3, take the formal parameter of this procedure and create a binding for it in this frame to the value of the argument passed in. Step 4, take the body of that procedure and evaluate it with respect to this new environment. Plus 1 and square of y, all done with respect to environment E1. Again, notice how we reduced the evaluation of one compound expression with respect to one environment to a simpler compound expression with respect to another environment. As before, it's a compound expression. We've got to get out the values of the sub-expressions. The first one is to get the value of plus with respect to E1. As before, that's the name rule. There is no binding for plus in E1. We go up the enclosing environment to the global environment and find the predefined binding of plus to the primitive addition operation given there. Getting the value of 1 is just a number. It gives us back 1. So all we have left to do is get the value of square of y with respect to E1. And that is itself a compound expression being evaluated with respect to this new environment. So we'll complete that on the next slide. To complete this evaluation, then, we need to get the value of square of y with respect to E1. And here's just a repeat of the environment structure we've developed so far. Well, let's do it in steps. Again, we've got to get the value of each of the sub-expressions, now with respect to E1. So we get the value of square with respect to E1. This is a little different than last time. We start in E1. Since there's no binding for square there, we go up the enclosing environment frame and get the binding for square from the global environment, therefore returning the appropriate procedure. The second sub-expression is y, so we need the value of y with respect to E1. And our name rule says simply look that up with respect to this frame. It's bound there, therefore return the value 4. So we're set for our big rule again. We have the application of a procedure, one of those double bubbles, to a set of arguments. So step 1 says drop a frame. Extend that frame into an environment by having its enclosing environment pointer be the same one as that specified by the procedure, which says we want this one. Notice an interesting point here. This new environment, E2, is scoped by the global environment, not by E1. You might have thought it should be E1 because that was where we were doing the work, but remember the rule. The enclosing environment is specified by the procedure being applied, not by the frame in which we're doing the work. Step 3, create a binding. That is, take the formal parameter of the procedure, in this case x, and bind it in that frame to the value passed in, which in this case was 4. And step 4, with respect to that new environment, evaluate the body of this procedure, times xx. So we've reduced this now to multiplying x times x within environment E2. So now we're almost done. We've got to get the values of each of these sub-expressions with respect to E2, but that's easy. We look up times, going up to the global environment to get the multiplier. We look up x in this frame, both times it's 4, and therefore we're ready to complete the process, applying this primitive procedure to those values. That, of course, returns 16. And remember what started all of this. That value then gets passed back up to where we came to when we started on this slide, which is adding 1 to the value returned by square of 4, or square of y in this case, which gives us back an overall value of 17. I know there are a lot of details here, but again, if you step through this carefully, you'll see how the rules for the environment model very mechanistically specify exactly the order in which to evaluate the expressions and how to look up the bindings of variables in the appropriate environment in order to make sure each expression has, in fact, a legal value. So what should you take away from this? Well, the key point is to see how, as we've said, these rules for the environment model specify almost everything we need to know in order to understand how expressions get evaluated. It doesn't quite do all of it. In particular, it doesn't show the complete state of the interpreter. In particular, it doesn't tell us what are the pending operations. And we saw that in the last example, where once we got that value 16, we had to go back and remember who was asking for it in order to complete the computation. Other than that, though, it really does specify the rules. Second thing is to notice how the global environment will contain, as we said, all the standard bindings, the things that come built in as part of scheme. And we've really omitted those from the drawings we've used so far for the environment model. The third thing that we want you to see is how it's useful to link the environment pointer of each frame to the procedure that created it. That way there's no confusion about who is going to use that frame. And in particular, notice how the frame has as its enclosing environment pointer the thing that the procedure says it should have, not the frame in which we're currently doing the work. Nonetheless, if this is unclear, go back and look at those examples again to see how, in fact, these rules very clearly specify the evolution of evaluation in this new model. Now that we're reasonably comfortable with the environment model, let's go back and tackle what started us off in all of this. Remember this example from the beginning of the lecture? Counter, or something created by makeCounter, was a little thing that should count up from a number. Every time we applied that procedure to no arguments, we'd get the next number up in the sequence. And we wanted to understand how evaluating the same expression could give rise to different values, and how, in fact, creating the same expression could give us different objects out that had different behavior. Let's use our model to see how to understand this computation. So here we go. Stick with me, because I know there's going to be a lot of details, but you should be able to follow all of this. Let's evaluate the definition of CA to be the value returned by evaluating makeCounter with argument 0. All of this done within the global environment. And here is, in fact, our structure for the global environment. We've already got a definition for makeCounter in it. It just points to that procedure object we got when we would have evaluated the define on the previous slide. Well, to do this, we know we need to get the value of applying makeCounter to 0. MakeCounter we know is a procedure, so the next set of stages we actually know. We're going to drop a frame, create it into an environment by scoping it by the enclosing environment pointer specified by the procedure application, and within that frame bind the formal parameter to the argument passed in. So here's the structure we would get. This is just like what we did before. Now, watch very carefully, because notice what we have. We now have an evaluation of the body of that procedure with respect to an environment. And what's that body? It is itself a lambda. Lambda of no parameters, set bang a bunch of stuff, then return the value n. And we know what that says to do. It says evaluate the lambda. In other words, create one of those double bubble structures. The code part is just the formal parameter, in this case nothing, and the body is just the set bang of a bunch of stuff and then the value of n. That's specified by the details of the lambda. The key thing is, where does the second part of the double bubble go to? What's the environment pointer we want to use? Right, it points to E1. And it does that because that's the environment in which we were evaluating the lambda. Notice this is a different structure than we've seen before. For the first time, we have a procedure whose environment pointer points to a frame or an environment other than the global environment. And in a second, we're going to see why that's crucial. Now remember, that red object there, that double bubble, is the value actually returned by evaluating the procedure, or the body of the procedure we applied. So that's the value returned by make counter of 0. Therefore, we can complete our definition. The binding for CA up in the global environment, since that's where we were evaluating the define, is now created. And that variable points to the object returned to by make counter, which is that procedure object. This is a useful structure. The variable CA, which is available to us in the global environment, points to a procedure, much as earlier things did, but notice that procedure has nested within it an internal environment. Its environment pointer points to an environment that is scoped relative to the global environment. Okay, having created this procedure object associated with CA, let's look at what happens when we apply it, when we evaluate it with no arguments. Here's just a recap of the environment structure. We have the global environment with a binding for CA. It points to a procedure object whose environment pointer points to a new frame or a new environment, E1, which is scoped by the global environment but contains within it its own primitive variable, N. Now the value of CA is just that procedure, so we're going to apply a procedure. We know what the rule says. Drop a frame. Within that frame, bind the formal parameters of this procedure. There aren't any, so there's nothing to put in the frame. And relative to this new environment, evaluate the body of the procedure, which says we're going to be evaluating that set bang of N and then the actual expression N with respect to E2. And notice the structure here. We now have a frame E2 that points to a frame E1 that points to the global environment. Okay, well we know what a set bang does, but let's be careful. First, we're going to get the value of plus N1 with respect to E2, which means we look up the value of N with respect to E2. It's not bound there, but we go up a level and find it with respect to E1. Aha, its value is 0. So we add 0 to 1, getting 1. Notice how that local frame has captured N for us. Given that, we now evaluate the set bang with respect to E2, which says, starting in E2, trace up the environment chain until we find a binding for N, which we find in E1, and change it there. Change it to the new value, which is 1. Having evaluated that part of the body of the procedure, we then evaluate the next part, N, with respect to E2. Same rules, chase up the chain till we find a binding for N. There it is as 1. Return that as the value. And that, of course, was the value we wanted to return by the overall application of CA. That's the value of the last expression, which returns a 1 at top level. The key thing to note here is how that local frame, E1, captures some state information that's accessible only by this procedure. Calling CA gives us the ability to get this value of N, change it or mutate it, and then return that value. Okay, let's see now what happens if we call it again. We should expect to see this behavior of it incrementing up. So let's evaluate CA one more time with respect to this environment. And here we just repeated the structure we got when we did the previous evaluation. N has been mutated from 0 to 1 as part of that process. Well, the value of CA is just that procedure. We're applying it, so we know what the rule says. Drop a frame. Scope it with the same environment pointer as the procedure object, which again says we're going to E1, as we did before. There are no parameters to bind in the frame. So evaluating CA with respect to the global environment reduces to evaluating the body, set bang of N plus N1, with respect to this new frame E3. Well, we know what happens. That's what we just did. It's going to go in and mutate the value of N to be 1 more than what it was, changing it from 1 to 2 in exactly this frame. And having evaluated that part of the body, we now take the second part of the body, the expression N, evaluate that with respect to E3, chase up the frame, find the binding, and return that value 2. And that, of course, is the value of the last expression in the body of CA, so that's the value returned by the whole thing. And thus we see how this local piece of state now allows us to have a procedure which, when evaluated in successive turns, returns a different value. So our environment model helps us understand how one counter, CA, can have some local state that it can keep mutating so that it can return a different value each time it's evaluated or applied. Now, let's see what happens when we call make counter again, starting also with 0, but giving it a different name. And just to recap, here's the environment structure we have to this point, with that procedure CA pointing to the procedure shown here, and with local state now having N equal to 2, because we've evaluated it twice. Well, we want to apply make counter to 0. We look up the value of make counter with respect to the global environment. It's a procedure. 0 is 0. We're applying a procedure. We know what to do. Step 1, drop a frame. Step 2, convert it into an environment, scoping that frame with the same environment pointer as the procedure. So this one, note, will point up to the global environment. Step 3, bind the formal parameter of this procedure, n, to the value passed in 0. Notice this is a different n than what we had before. This n lives in environment E4. The n we had for CA lives in environment E1. So we have different bindings for the same variable in different environments. Now, relative to this environment, evaluate the body of the procedure. And remember the procedure we're applying, it's make counter. So we're going to evaluate that lambda expression with respect to E4. And we know what evaluating a lambda should do. It creates a procedure object, a double bubble. The parameter or code part of the thing points to the parameters, which are none, and the body, which is at setBang. In fact, it could point to the same one we had before. The key point is, where does the procedural object's environment pointer point to? To the environment in which it's being evaluated, to E4. So this procedure has a different scoping. It's going to capture E4 with that version of n, which is different than the one we had before. And finally, that's the value returned by applying make counter to 0. That's the body of the thing, so that procedure is returned as value, and therefore the definition creates a binding for CB up in the global environment to that new procedure object. Look carefully at the structure we have here. We have CA pointing to a procedure object that inherits a frame E1. We have CB pointing to a similar procedure object that inherits a frame E4. They have different scopings or bindings for the parameter n, and that's going to allow these things to behave differently. Now, let's finish our understanding of this process by looking at what happens when we apply CB within the global environment. And remember, here's the environment structure we have. We have a global environment, we have a binding for CA to one procedure object with its own frame, we have a binding for CB to another procedure object with its own frame. What happens when we apply CB? Well, the rules make it very clear. We take the procedure object associated with the binding for CB, we apply it, which says drop a frame, scope it by using the same environment pointer as the procedure object, which says E5 will be scoped by E4. Not E1, not global environment, E4. This says, using exactly the same reasoning as before, that the value of n that will get mutated is the one that is seen from E5, namely the one sitting in E4. So it gets changed by 1, and then we return that value, which says the value of the overall expression is just 1. So what was the point of this long, drawn-out exercise? Part of it was to let you see how the rules for the environment model evolve. They specify what happens with the computation now. They specify how expressions get meanings assigned to them through a very mechanistic set of rules. But the second point was to let us understand things that involve mutation, and in particular, mutation associated with procedures. So think about what happened with our little counter example here. Here's the environment model that we had. And notice that there's a structure associated with it. What does CA look like? It's a name bound in the global environment that points to a procedure. And more importantly, that procedure has as its environment pointer a pointer into a frame, in this case E1, that has some local state in it. Now, the only way we can get at that value of n is through a procedure whose environment pointer through some chain of events points into that frame, or in this case only through CA. So this structure, this pattern, is a common pattern. And in fact, when we evaluated make counter again and gave it, the result returned by it rather, the name CB, we created a similar pattern, but now with its own local state. So each of these names specifies a procedure that has associated with it some information that belongs only to that procedure. This kind of framework, that is, procedures that capture local state and can manipulate that local state, is going to be a very useful programming tool, as we're going to see in the next few lectures. So as you step away from all of this, here are the two rules or the two thoughts that we'd like you to leave with. Note that environment diagrams or environment models are very valuable, but they get complicated quickly. They're really meant for the computer to follow, not for us, and we're going to see that when we use those to build an evaluator. The second and most important thing was the example we just saw. A lambda inside a procedure body captures the frame that was active when that lambda was evaluated. That means we can use this to store local state, and that's going to allow us to build a whole new set of programming tools, as we're going to see in the next few lectures.